All right. Um, cool. So again, just want to ask real quick. We understand how the hash function. I mean, not that we know how to build one, but we understand how it works and what its purpose is.
In a general sense.
Yes. You understand how we use that to index into our array. Right. Yeah. Again, like really, the implementation is gonna get tricky, you know, and like stuff's gonna come up. Of course, it always does. But really, it's like as straightforward as that. Instead of getting your keys by just a number you choose, you get the keys to your values by running it through a hash function. The Python dictionaries that you see, or JavaScript object dictionaries, whatever you see where they're using a hash table underneath, they just have their own hash function, right? And like they'll use that. But it's really as straightforward as that.
So where does the linked list come into play?
Glad you asked, because what's coming up next is the birthday paradox. So are you guys familiar? Huh?
Collision.
Yep, exactly right. So are you guys familiar with the birthday paradox?
Yeah.
If you're talking about how I keep getting younger every year, then yes, I'm familiar with that.
Listen here, Dorian Gray.
That's the Benjamin Button one, yeah. The wrong one. Here we go. Let's see.
You must be Asian.
Possibly.
All right. So, of course, right? Say for birthdays, right? If we have 365 persons, right? So if we have this, I guess let's do leap years, right? So it's 366 days in a year, right? If we have 367 people in the room, then you're obviously guaranteed that someone's going to have the same birthday, right? Why is that? Because if there's 367 persons in the room and there's only 66 possible birthdays, right? Oh, good, I actually used the right numbers. Then even if the first 366 persons have a different birth date, every single one, which would be amazing, you know, the 367th person, they have a birthday too, and it has to land somewhere, right? So like, there's going to be some collision there, right? If we think about this in terms of our hash table, right? You could make a hash table where your that is 365 items long, and then your key, your hash function, right, is you get your name, and you use your birthday as your birth date as the index in your array. So I don't know. My birthday is July 30th, right? So I'm guessing it would be somewhere like the 210s, something like that. So like my spot in the array would be 210. Somebody who's born July 1st, their spot would be January 1st. So like the very first spot in the array, right? But so if there's 367 of us, one of those is going to get mixed, and we're going to have what we call a collision, right? I think you saw it in the video. And basically what that means is we have two persons, say, I don't know, it's actually really funny. So me and my uncle and I, we both have, what's his name? We're both born on July 30th, right? Right. And so say, I think that number would translate to something like 200 and let's say 210, just to keep it easy. Then you'd have to store both of us in the same spot, right? Then like, how's that going to work? If we're both giving out the same key, then who's the one that who actually gets the spot, right? And so you might think it's not that huge a problem because like whatever, you know, if there's 365 spots, you can just make it, let me check, make it bigger. Let's see, 14% chance two people in this room have the same birthday. Yeah, 14% looks like a high number, right? But this is the cool, this is the weird thing about the birthday paradox and why it applies to us. 99.9 probability is reached with just 70 people, right? So that means that in our lambda cohorts, all the cohorts you've been through, whether it's 70 people, more than likely, I mean, maybe not you in particular, but there's at least one pair of persons there that share the same birthday, and with just 23 people, right? So I mean, we're about to get there. There's a 50% chance that some of these people share the birthday. That's 23 people in an array of 365 slots. 211th, so 210th. Oh man, I missed it by one. Because since we're indexing the array, then you have to subtract one. That's where I got the track. So yeah, it's gonna happen. So the reason we don't concern ourselves with building hash functions is one, well, if they work, then that's fine. We don't have to worry about it. But the other is it takes some like ingenuity and some math and some knowing what you're doing to make sure that your hash function is what we call uniform, right? Uniform meaning it's hopefully going to spread all of the keys among the all of the array instead of having them all the same one, right? So if you think about what a good hash function is, right? Great hash function. Oh man. So we have great hash functions here on the right, and we have horrible hash functions here all the way on the left, right? Horrible hash functions, think about them in like a vertical sense, right? Like all of their meaning, whatever you pass into this horrible hash function, you're gonna get the same exact value back. Like which might happen, like if we run enough names here in hash.max, it's exactly what I mean, right? So like if we had 14 names right in here, and our array function only had space for 12, then there's gonna be some repeats, right? No matter what. But there, depending on the hash function, like there could be all of them repeats, right? Like that would be the worst case, and so there's no use for your hash function because then you have to search for everything in the same spot. And then great hash functions, on the other hand, just like spread it out as much as you can. Now, writing great hash functions is really hard. One, because you never know what the values are going to be beforehand. So you might, your hash function might be great for some values, but really bad for others. And yeah, basically, since you have no idea what input you're going to get first, you never know. So what happens when we run into these chances, right? Like eventually these are going to happen. You saw there's a few different ways. I'm not too familiar with most of them. The one I do know is we used Michelle. I think you mentioned it. What was the other structure we used for hash functions?
Or linked list?
Yep, exactly right. So what happens? Say so 211th. This module of 211. By what size of array? 9, actually 10. So very easy. 1. All right, that's actually quite a bit easier. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so that's 10. So both me and my uncle, we'd go in spot 1, right? 0. So this is 2. We'll leave it like that for now. So what we do in hopes that we're not linking too many functions is say we run my name first to the hash function and we get a 1. Then I will store myself there. Let me make myself a little bit smaller so we can store myself in the box. Here it is. So I'm stored. Nice, I did it. So we're there, right? And then once we run through my uncle again, he's gonna try and show up here at 1, and he's gonna see that I'm here. There's no space. So it's pretty simple. The only thing we do is we create a node out of him and myself, right? And we store ourselves both here in this linked list. And so so having a stored there, now we, if we could store here as many people. Let's say we have someone else. So we had someone with the birthday on day 231st, right? So let's say that number, or I guess 341st, right? Like they're gonna get spot 1, right? So this other random person, let's say, can make up a name here. Say Carlos, right? We get Carlos here, and Carlos is 341st day. That's going to be about 14th of December, right? 14. And so we just, if someone else just happens to be here, we just add them to the end of a linked list. The same way we do appends with linked lists. You've done linked lists before. We just add those here. And then if we're looking for Carlos, then Carlos we're going to run Carlos through the function. We're going to check and see, all right, is Carlos, we're going to check, is there one item here, or are there more items? Seems to be like there's more. So we're not sure if Carlos is red one right now. So let's just check again. And then we check Carlos against each of our items here in the linked list. And then when we finally find Carlos, okay, now we can access the value. And yeah, that's pretty much so. So like that's one way to get around. There's other ways. Another way is so looking for so say if my uncle came in after I'm here, we could look to the ones around me and see if they're empty, and then we place them there. Same thing for Carlos. A few other ways, but this one is one of the most straightforward ones. And there's two cases that can happen, right? So we have the case where it could be a horrible hash function, and then turns out that everybody comes into the one, and we just have like a huge linked list of people all in here, or we could have a really good case and we never have to use the linked list.
I have a question.
Thanks. Yep. So
I kind of missed why Carlos is in this linked list if he doesn't have the same birthday.
So if your birthday is December 6th, I was just getting that by Steve. And say we're just doing modulo by 10. So let's see.
Oh, okay. So, okay, got you. Okay.
So if December 6th is day 341 and we do modulo 10, he's going to be a 1 as well.
Yeah, I get it.
Yeah.
Cool.
All right. Now,
basically have to start off with our array being an array of nodes for a linked list then.
Yeah.
Okay.
Yeah. Think about it. I'm not entirely sure right now, and I'm sorry I don't have the answer, but it might make a lot of sense to then, if you're going to do a linked list, storing the name in the node, keeping the key and the value, so where you can compare each one. But I don't think you'll have to worry about this until tomorrow. So I'll come back to you guys on that.
So when you're adding on to you have its position in the array because you ran the key through the hash, and then you have the index, and then it goes down the linked list. Will it always add to the end of that linked list?
I mean, it really depends on how you implement it.
Somewhere in the middle of that linked list.
So it really is up to you, right? Like if you're building your hash table, you can do whatever you want. The most, what I think is the best option is just adding it to the end of the list because
Right.
that's O1.
So when you're searching through, for example, I want to search for Carlos's birthday. Um, I would run the key through the hash so that I get the index in the array-ish part of it, and then is there a way to go straight to Carlos, or do I need to go one after the other searching for Carlos through the line?
So it's a linked list. What do you think? What would you guess? Can you get straight to Carlos, or would you need to go
I
through?
would guess that you have to go one after the other until you find him.
Yep. And so that brings us to another thing. So in our best case scenario, right, with a great hash function, if we search, so like there's one person in every single bucket, right, every single spot in the array, and so what's our time complexity to find someone?
Oh, 1.
Yep. Now, in the worst case, right, where we have all of the names that we put in, like everybody's birthday ends with a 1, right? So they all get assigned to spot 1, kind of like we see here. What's the time complexity to find someone there?
Oh,
In factorial. Just kidding. Yeah, I think it's in.
Yeah, it's all in. Right, because you get to this one here, and Carlos might be all the way at the end. So if there's a million items and all the million items, they're all stored in bucket 1. Even though you got to the magical index where you could get to it right away, you still have to search through all of them to see if they're there. And so, of course, we don't want this to happen. So, programmers, being the really smart people that they are, they figure out a way to keep a number where this doesn't happen, right? So if our array is pretty empty, or like if our array is completely empty, or there's like one or two, like if it's completely empty, then we're guaranteed that wherever our new person comes in, no one's going to be there, right? Why? Because it's completely empty, so that's not a problem. If our array has 100 buckets and we only have like, I don't know, 3 or 5 items filled, then we're still pretty sure that we're not going to have collisions, right? They might happen, like who knows? It was me and my uncle there. We were the first 3 persons in this array, and we're all in the same bucket. But chances are it's not really going to happen, right? But then we saw it with the birthday paradox, right? As you keep adding people, with just 23 persons, right? So when you have 22, if you add the 22nd person, right, there's a 50% chance that you're gonna get a collision, right? And so as you keep adding more and more numbers, more and more people, the probability of a collision starts getting higher and higher. And so we have a very precise number for that, and that's called a load factor. Pretty sure you saw it in the video, but I can't recall right now. And so this load factor, let's give ourselves some more space here. Okay. And so the way we calculate this load factor is, is we do the number of items stored times the number, divided by the number of buckets, right? And if you think about it, this makes a lot of sense, right? Because say our number of buckets is 100. It's 200, so it's a simple number, right? Right. If we have 10 items stored, right, right? Then our load factor is going to be 10 items stored divided by 10 number of buckets. So our load factor is going to be 0.1. Let me just make this consistent so you don't get lost. So our load factor is going to be 0.1, right? 0.10. So that means, you know, there's not that many there. We're pretty sure that it's we're not going to get any collisions anywhere soon, anytime soon. So we're not too concerned. If we bring it to 35, then, you know, our load factor then is 0.35, right? That's pretty simple math here with the 100. Now, since this is a hash table and not an array, and we have a linked list, we can store more items than there are buckets, right? Like we could store, say, 150 items, right? And so how would that have to look like, though? Well, you know, all of these would be filled, and then some of them would have extra items, kind of like what we see here, right? Like at least all of them filled once, more than likely. Not necessarily, but more than likely, all of them filled up once. And then half of them have an extra friend they're hanging out. So that's 1.5 for every right, for like every 2 buckets there's 3 people. And so our load factor looks like this, 1.5, right? Now the whole point of having this math is it gives us somewhere where it gives us like a hard limit to where we know where to optimize and when to change the size of our hash table, right? Because so if we have 10 items and our load factor is 1, then, you know, we might not want to spend too much time resizing the array, because resizing the hash table array means, you know, we have to copy everything over. We have to allocate new memory for the array. Then we have to, what's the word? Not just copy everything over, but we have to run everything through the hash function again, because given that our max has changed, remember, right, that the max is what makes the changes. If remember, we copied Chad's numbers and he always got the same number because it always ran through the hash function. Well, now that the size of our array has changed, right, we're going to get different numbers. So resizing is useful, but we don't want to do it often, right? We don't want to do it every time we add an item, because otherwise then we'd be spending a lot of time copying everything over and doing everything one more time. So we don't want to resize to avoid collisions when the load factor is low, because, you know, it doesn't make much sense. You know, we're probably not going to get there. But then we also don't want to wait until our load factor is 1 or greater than 1, because then we're guaranteed to have a collision, right? And so, yeah, pretty much. So you can use the load factor to decide when you want to resize your array, when it's worth doing. It's a pretty arbitrary number, really. You can choose whatever you want. I know Python's load factor for resizing arrays, the hash tables, is about 0.07, right? So for every 100 buckets.
0.07?
Sorry?
0.07?
I said 0.07, right?
That is what you said.
That is what I said. That is not what I meant. Thank you. Yeah, no, 0.07 would be ridiculous, right? You have like 7 items per 100. No. 0.7. Right? So for like every 100 items, you know, if it were 300, then this would be, you know, 210. Whatever. Like the only thing that matters is the proportion, right? Not the total amount. And so, yeah, this is, and so the Python underneath the hood has a check, right? And so it has the number of buckets, and it keeps checking, you know, when the items of numbers stored are, if that division is greater than 0.07, then we'll resize the hash table. Otherwise, you know, we just lose out on space. All right. Any questions? Is linked list chaining for collisions and why collisions happen, load factor, is all this clear? Kinda, sorta. All right, cool. So let's see. For today, let's just get over the hash tables, and then if you guys want or have the time, we can get into solution code. I would read through these once again. Obviously, I like the way I explained it, but it's always great to see different ways of explaining things. This is also a lot shorter, so everything should be easier to synthesize now. Yeah, your assignment is pretty simple. Just finish the basic hash table, basic hash table. Let's have a quick look at what's inside. Here's your pair, right? These are again in case of collision, so you can link them. I don't think you'll be doing handling collisions in this basic hash table. I think that's going to be meant for tomorrow. Again, as you see, here's the hash function. All you have to do is get the insert. Should be pretty simple, right? Connor, how would you? I mean, obviously, don't write out the code, but what's like the plan to fill this out?
What is HT of the basic hash table?
Oh, that's the here. It's just the variable name for the.
Yeah, that's just what it's called. So you would get your key, which would probably be the name, which would go through the hash function. Then you can insert that into your table. Then insert the value at that key as well.
Yep, pretty simple. Run this with the hash function, insert those in the hash table.
Are we populating? Never mind.
So this is reminiscent of Tuesday's homework. Just using a hash for to get the index, sort of.
Yes, it should be pretty similar. And the reason it's pretty similar is because really all that hash tables are is glorified arrays. Like they're arrays that work almost exactly like arrays. Like everything's pretty much the same. The only difference is in order for you to get your index, you use a hash function. And that's it. A few hints, right? You're gonna have this basic hash table. Now, usually arrays, like we mentioned at the very beginning, you can't really, add stuff in the middle or here and there. So think about whether malloc or calloc, right? Whether those would be more useful in this situation. Let's see, hash table remove, hash table destroy, hash table retrieve. Chad, how would you go about hash table retrieve? What would that kind of look like? Obviously, don't tell us the code, but like, what's like the general plan? You're muted if you're. There we go.
So retrieval, you would so you have the key. You would run the key through the hash or the hash function, match it with the index, and then return whatever value is at that index.
Yep. Again, like really pretty much as straightforward as that. All right. Cool. Any other questions, I guess, regarding hash tables for now? Otherwise, we can start looking into the solution code for yesterday. All right, cool. Then let's do something then. Since we're only doing solution code, right, and this is stuff that some of you might have solved yesterday. If you guys feel pretty comfortable and you're done, this is going to be recorded anyway. So if you want to check it out later, you can leave now. You just get an earlier lunch and start working on it and start working on the homework for today. If, however, you do want to stay and check out the solution code, we're going to run it through. So I guess classes officially over right now. Those of you that want to stay, feel free to stay. We'll go through the solution code. Those of you that want to gather some extra time and just start working on the homework for today, or I don't know, I mean, it's your day, right? Whatever. You have an extra 15, 20 minutes. All right. So if you're staying, let's get started. Let's open up a new Python tutor. All right, so let me bring. Just bring out the code from yesterday. Whoa. All right, so yesterday we did create, destroy, append, and read. Now for today, we're gonna do array.insert, array.remove, and array, oh sorry, resize array. All right. So let's do insert first. And insert I'm interested in because insert we could do something interesting with append. All right. So anyone. So what do we want to return for insert? Do we have any return values that we want to get, or do we just do void? What's the best strategy here?
I think it's a void because we don't return anything. We're just inserting something.
Yep, that's pretty right. If you wanted to, you could have a return value where you get it, but really you don't need to. All you want to do is insert the array and just trust that it works, right? What do we need in order to insert into the array? There's two things. There's, well, actually three things we need.
And the index we want to insert at.
So I heard the index. What was the first thing you said?
The thing you already put in.
Oh, the array itself. All right. And then obviously, of course, we also need whatever element we want to pass in, right? So the first thing we want to do is we want to check and make sure that we're inside, whether we're not indexing outside of the array. So if array is greater than count, why am I using count here and not capacity?
Because count is the actual number of elements in the array. Because if it was greater than a count, we could just append. But if we're putting something in the middle, then we have to pick a number between 0 and the count.
Yep, exactly right. Count is always going to be less than the capacity, and we might be inside. So again, we might have an array that has a capacity of 10, but we only have 5 items, and then we're trying to insert in position 8. We're still out of index with our array, right?
Your if statement needs a greater than symbol.
Yeah, this is saying nothing. Thank you. All right. So yeah, that's why we use count instead of capacity. All right, next. So remember, what's the worst case for insertion? Like when does insertion turn into O of N?
Inserting at index 0.
Okay, that's 1. And if we're adding at the end?
If we're adding at the end and we need to resize.
Yep, exactly right. And then when do we resize? If the capacity of the array is less than or equal than our current count. Really, it should always pretty much stop at count, but you want to Okay, in case something goes wrong, you want to make sure to check for those as well. And then we've already implemented resize before. Well, sorry, we're going to implement resize in a bit. So technically for now, this is resize the array. Yeah, we're not going to do all that here. But then what we want to do, of course, is resize our array here. So now we just, so it comes back with more capacity. We'll comment it out for now. Just to be consistent, since right now we'll still don't have a resize, right? All right, so if capacity is greater than count, then we need some more space. We just give it more, pretty much resize what it's doing is just giving us more capacity. All right, and then now, if we're inserting at the end of the array, that's pretty easy, right? There's nothing we have to do. This is just an append. We already have this. If, however, we're inserting at the beginning of the array, what do we need to do with all the items before we insert the new item?
We have to shift everything if it's like in the middle, or unless it's, well, even if it's at the beginning or any place except the end, we have to shift everything to the further end of the array.
Yep, that's right. So before we can get the item in its place, we have to give it some space, right? And so it's pretty simple. So there's quite a bit of ways to go about it. The way I like doing it best is I have my array here, and this is full of, some other values. 4, 63, right? What I find simpler and just like less confusing overall is starting from the end and then, copying this over, right? And so I can start here, copy to the next one, copy 54 over to 63, 34, copy that over to 50 to where 54 was. I guess copy Luisan to where 34 was. Copy, say we're inserting at the beginning, right? Copy 12 over to where Luisan was. And then here we can just, insert the new item on top of this. So let's do minus 211. Right. This just makes this, just going from the right to the left just makes it so that it there's no toe stepping, right? One thing you can run into if you try to go the other way is, say I want to copy 12 over to Luisan. Oh, right. I want to start at the first spot and copy over to the right. I'll run over this and then I'll have lost Luisan, right? Now I won't be able to copy it, and then you run into the kinds of error like that. All right, now I'll copy what's in 1 to 2, and then copying what's in 1 to 2 means I'm just copying 12 again, right? If then I want to copy 2 to 3, then I'm copying 12 again, and then you end up like all of them are possible, right? All of them can work. I just like going from starting at the right and pushing them one forward. I just feel it makes it a lot easier. All right, and so we'll do it that way. So that means we're starting at array.count, right? We're starting all the way to the right because the one at the end always needs to be moved. Now, here, should I write 0 or should I write index? What do you guys think?
Index.
Why index and not 0? Why don't I want to loop through the entire thing?
Well, unless you always want to insert something new at index 0.
Yep, exactly right. If I want to insert something at index 2, then once I move this guy over here and this guy over here, remember it's technically copying, right? But just for quickness sake, if I keep moving stuff here to the right and then I insert a 2, then I'm gonna have, like an empty spot at space 0, and I'm gonna have lost some items here at space 2. So I want to stop at where the index is. I want to stop at where I want to insert the stuff. So that's why I use index here and not 0. And then this one's pretty easy, right? Array elements I. Why should this be I? Should it be I plus 1, or should this be I minus 1? What should this be?
No, it should be I, and then the value you're setting it to. Hey, close that bracket.
No, I haven't closed it yet because we're still deciding what is this going to be. So why I and not I plus 1 or I minus 1?
It ties back to the fact that we're starting at the end of the array. The last element in there, array.count, is guaranteed basically to, unless you mucked up your code, the index at array count is going to be empty.
Mm-hmm.
So naturally copying something into that first and just gradually shifting everything to the right one is going to be the easiest way to not step on any toes as you're doing so.
Yep. Let's just let's start real quick. So
So in this particular case, it'd be like array arrow elements I equals array arrow elements I minus 1.
Yep. And the reason is, so not right now here we have 5 elements, right? So array count is set to 5. Right, so we're guaranteed that if we do array at array.count, right, at 5, we're gonna get, yes, like you said, 1 space after the final one, after the final item, right? This is index 5 right here, and it's empty right now. So if we do array I is set to array, that's the one, array I minus 1, it means that at array 5, we're setting array 5's value to whatever is in at array 4, right? So then when we're at 4, whatever is at array 3, we're going to set that at array's 4 value. And that's basically what we're doing, just copying over right to left. So array elements at I is set to the array elements I, I minus 1. And all right, we copy everything over up until the index, and then something we were talking about yesterday. Again, not entirely necessary to make a copy, but very recommended. Just keeps your code safer. We created a copy.
I was having some weird issues with string dupe yesterday. I was getting like random what's the term I'm looking here? Seg faults when using it.
Reach out to me after lunch and let's have a look.
Using basically the exact code you have on line 92.
We'll see. It might be something with what's being passed in, or maybe you forgot to include. Did you include the headers, the string.h?
I believe they were included already, but let me double check.
Might have been.
Yeah,
let's check it out after lunch. We can probably do that, get it solved. But yeah, here's your array insert. So again, check to make sure you're inside the index. We check to make sure we don't need to resize it. If we don't, we keep going. If we do, we just resize it, that's fine. Copy everything over from right to left all the way up to the index. And then at that spot in the index, we just add the new element, which we made a copy of. Pretty simple, right? Now, the thing one thing I like about having this insert is that for your append function, instead of writing the whole thing, you can just also do array.insert, and then array.insert takes an array, an element, and an index. So you do array, the element you're passing in, and then as an index, you simply use, anybody want to guess?
Array arrow count.
Yep, just the last item, the last spot. So one spot after the last item in the array, right? Remember we saw from count. Count is one spot after the last item in the array. All right. So both of these work, right? All right. Now we said append. Next is remove. So let's do remove. All right, so we'll move through a little bit quicker because I know we're running out of time. We want to remove the array. Obviously, we need the array where we want to remove the stuff from, and then the element that we want to remove as well. Now let's see. So we'll start with this. So int removed set to 0. We're setting this as our Boolean value since there's no true or false in C. We just use zeros and ones. And then to our for loop here, gonna go all the way to count. All right, searching through the entire array. All right. So we let's see. So what we do is, I guess it's sort of hard to explain in these pieces, but so if we've already removed an item, then we wanna bring the items back to where they actually fit. So just tells us if we've already removed the item. So if we've already removed the item, then everything that comes after that, we just move back one to the left, right? So setting the item before it to whatever is after it, just making a copy, moving to the left. This is going to copy everything over. That bracket is not supposed to go there. Pretty straightforward, right? We're moving it around. If it's not, then we need to check and see if they're the same. We use a function here. I think some of you are familiar with it already. It's called string comp. This compares two sets of strings that you pass in. If they're the same, you get a value 0. If they're not, you either get 1 or -1. I'm not entirely sure right now which one is which, but that's easily searchable in the docs. You compare the first element to this element, right? If they are the same, then yes, of course, we want to get rid of it. So we'll free it. Second. Free to make sure that we're not and we're not having any memory leaks, right? Remember, the reason we're freeing them in this particular implementation is because everything new thing we add, we're string duping, and string dup uses malloc under the hood. So we need to free each one of them, right? And then really easy, we can just set remove to 1. Now, what's going to happen now that we said remove to 1, we still haven't got rid of the item, but when we loop through again, right, at I, so the next one, we're going to set, so let's see, we had an array here. Right? This was the element we wanted. Let's do it another color. Let's do it in orange. It's for the element we want, right? So then now we change removed to 1. And so this is when I was at this spot, right? Like, now in the next iteration of the for loop, when I is here, we're gonna set I minus 1. So so if we're, let me make this black. Oh, so I was here. Right now, this is where we set everything. We freed it and we set remove to 1. And now that I is here, array of elements I minus 1. This is I minus 1. This is just going to get copied over. This is just going to be set to whatever is here, right? So this is going to copy this, meaning that we've effectively lost the item that was here, particularly also as we freed it, right? And then just copy everything over pretty much until we're done, right? Let's see, let's get rid of all those. Go back, and then right, once we're done, if I keep forgetting we can't do this here. You've removed, then and then we just do our cleanup rep array.count. We decrement this because now we have one less item, and then since remember we were copying everything over, right, from so moving left to right but copying back, we're gonna have 2 copies of that last item, right? So say this were our last one, then we would end up with this X value here and this X value here. We don't want to have that extra duplicate because that makes no sense. So all we do is set our elements at our new count value, last one, just set it to null. So now there's nothing there. Otherwise, in case we didn't remove anything, just printf standard error. Error, not an array, just some error, well, whatever you say. It's up to you how descriptive you want to be. Whatever you say, doesn't really matter that much. Yeah. Any questions regarding remove? I guess regarding insert as well, I forgot to ask.
I'm good.
All right, cool. And then finally, then all we have left is resize. All right, this should be fun. So let's see. So resize is going to be a void as well, because all we want to do, so we don't really need access to the new element. All we need is to resize it, right? Like all I want to know is that once this is done, my array now has more capacity than it did before. So I don't really need a return value from this. This is the array. All we need is the array itself, right? Whatever the elements are right now, I don't really care. Let's see. So the first thing I want to do is set the new capacity. I just have access to this now. I can use it anywhere else in my code. Capacity times 2. Simple as that. I saw a few of you do array capacity times 2 and size of. it's fine because it is going to make the capacity bigger, but you're not really getting what you want. So remember that when we set, go up here, when we're setting the size of our array in create, we're passing in just an int, right? And so that means if we pass in 10, then we're expecting capacity for 10 items. So the reason we multiply here in resize just by 2 and not make this by size of is, so if we do something like size of char or size of int, yes, we are going to get a bigger number, but you know, if size of let's say int is 4, then we're effectively just multiplying array capacity times 2 and then times 4 again. And so instead of going from 10 to 20, we're going from 10 to, what is this, 80 right away, which is fine. It's still a big array. It's going to do what you want. It's going to take a while to resize, but for readability's sake, it'll look like you're trying to do something here with the size of when you really aren't. Like the only thing you're interested here are the integers. So that's why, I mean, then if you wanted to, you could choose any number, right? Like it doesn't really matter. Just so adding this just makes it a little bit more confusing. Makes it seem like you're going to do something with this, or that it's relevant somehow when it really isn't. All right, so we keep it at times 2. We need to again reset our. We need a new array of pointers to strings so we can restore those again. Calloc. So cool thing now that we have new capacities, we can just pass that in right away, right? However many zeros we need. Size of char star here, because we need enough size for all of the pointers. Then we just simply copy elements into the array. So let's see, for I int I set to 0. I is less than array.count. Why array.count? Because up to this point, we're only going to copy the items that we already had from the past array. Notice it's not a new count or anything. We're just count from we're just copying the old items that we had from the old array. So all we need is up to count, right? We don't need anything more. We'd be losing out if we did anything less. And then just normal for loop increment by 1. Simple, right? New elements at I, just set what we'd had at elements. It's just copying everything over, pretty easy. And then free array.elements, so we don't get user memory. So the old array elements we're not going to use, so we want to free that so we don't get a memory leak. We don't want to free the elements themselves because we're still going to use the elements. We're copying them over, right? Even if we're just using addresses, but we still want those values. We don't want to lose those, but we do want to lose the old array. And then just update our current element. So now our elements is new elements. Set the array, and then capacity. The capacity we just set up top right here. No need to reset count because we still haven't added any new items, and it's the same amount of items. We haven't removed or added any new items, so we keep the same amount of items. And we're good. No need to return anything since, again, this is a void function. And if you see how we're calling it, just go on. Let me call it right here. All we do is resize the array. No need for return values. We're not asking for anything. All we want is the array to be resized. And that's what we're achieving right here. Just, again, new capacity, allocating enough memory for this new capacity and, you know, all the pointers that we need, copying everything over, freeing the old one to avoid memory leaks, and then just setting the current element, the current array's values to the new values. All right, For the few of you that are here, any questions? Are you guys good to go for lunch? I'll copy this into a Slack channel anyway in a few seconds. All right, then hope this was useful for you, for those of you that stayed. I hope this was also useful for those of you that are watching it on video. Have a good lunch. I will see you guys later.